So section 10.1 talks about correlation. So we're going to add that to the list of things that we can test. Now we've tested a lot of different things. We've talked about means, standard deviations, proportions. Now we're going to talk about correlation. Let me remind you of certain things here. For instance, what's the symbol that we use for the sample statistic? What symbol do I use there to represent the sample statistic? Anyone? Maybe this one, X bar. And how about our population parameter?
Mu.
Yeah, we use mu. Now over here for our sample standard deviation, what symbol do I use?
S.
S, excellent. Someone else here. Standard deviation is?
Sigma.
Sigma, wonderful. Population proportion, remember that one?
P hat.
P hat.
P hat. And then just P here. Now let's do the new one. The new one is correlation, which is going to be an R, and don't shoot the messenger. Rho is the new Greek letter here. So I tried to exaggerate a little bit. It looks a lot like a P. I'm not lying. So we've got the P for proportion, we got the rho, and then P is in p-value. There's too many P's going on here, but there's not much I can do about it. So what does correlation measure? Well, correlation talks about how things go together. And in particular, we're talking about really a linear correlation. So maybe I could put linear here as well. How well does a line represent the relationship between two variables? So let's take a quick look at our handout for that. That's something that you should have gotten out of the chat. So this one over here, the linear correlation coefficient. So we're going to denote that with R, our sample value, is a number that represents the strength of a linear relationship between two variables. Now, I'll give you a heads up that that linear correlation coefficient is going to be a value between 1 and -1. So the extreme values that you get out of this, right here, come on, let me try that one more time, are going to be when you have a perfect straight line, either going up or going down. So let's start with this one down here, when R equals 1. If R equals 1, then your data follow in a perfect straight line. That's when you get a R equals 1. Now that's a positively sloped line. If you had a negatively sloped line, then you're right here. R equals -1. But again, it's a perfect linear relationship. It's not very often that you're going to find R equals 1 or -1. Quite often things will be, not quite a perfect line, like maybe down here, where it's still close to a line, but it's not perfect. So R is close to 1. It's not perfectly 1. If that line happens to be sloped in a negative direction, then R is close to -1. But the farther away you get from a perfect line, the closer it's going to get to 0. So data like this, scattered about kind of randomly, all right, there's no correlation there. So you get a value that's close to 0. But let's look at this last graph here, F. And F is a little bit troubling because, I don't know, look at the relationship here. Is there some kind of relationship between X and Y? Well, yeah, there is. That looks like a semicircle to me. But here's the thing about R. R talks about the linear relationship. It's the linear correlation coefficient. And there's no line that can summarize this data. You can't do that with a single straight line. So that's why you're getting r equals 0 for this last one. There's no linear relationship. Okay, so let's talk about some of these relationships, some of the things about R. And again, what I'm doing here is what I did in the last section, which is to start with some of the kind of general questions in your homework. Now, what you're looking for is a relationship when something goes up, something else goes up. You increase your study time, you increase your grade. Or if you increase your exercise, you'll decrease your average heart rate or your resting heart rate. So those kind of relationships are things you can summarize with R. And let's take a look at this first one. 20 different statistics students are randomly selected for each of them, their body temperature in degrees Celsius is measured and their head circumference in centimeters is measured. For this sample of paired data, what does the value of R represent and what does the value of rho represent? So we've done stuff like this before, and it's not a bad idea when you're doing this homework problems to do a process of elimination. And I see something I can eliminate right away. This is something that we did just a minute ago. Let's take a look at this first statement. R is a parameter. Is that true? Is R a parameter?
No.
No.
No, R is our sample statistic. So right away, we can get rid of that. All right. The next one. R is a statistic that represents the proportion of variation in the head circumference that can be explained by the variation in the body temperature. And rho is a parameter that represents the value of the linear correlation coefficient. Well, R is a statistic, that's fine, but R has nothing to do with proportions. All right, that's a different symbol. That would be P hat. So I can eliminate that one. Let's move on to the third one. R is a statistic that represents the value of the linear correlation coefficient computed from the paired sample data, and rho is a parameter that represents the proportion. Man, did it again. They're throwing in this word proportion, which I don't really like in this one because they use P enough and that rho looks so much like a P. So let's nix that one. Now by rights, we should just put the D and then move on. Well, let's just double check it. R is a statistic that represents the value of the linear correlation coefficient. So we're okay there. And rho is the parameter that represents the value of the linear correlation coefficient that would be computed by using all of the paired data in the population of statistics students. So yes, D is the right answer there. Now, how much relationship do you think there's going to be between the circumference of somebody's head and their body temperature? Is there going to be some kind of relationship there at all? If you have a big head, you have a big body temperature? Small head, you have a small body temperature?
No.
Yeah, I don't think there's really going to be much of a linear correlation at all. So if there's no correlation, what value of R expresses the idea that there's no correlation?
0.
0.
0. Perfect. So a big fat 0 in here for the linear correlation. There's no correlation, that would be a 0. And let me see if I can do it this way. Put in a big 0 here. Okay. Last but not least, choose the correct answer below. The value of R does not change. All right, so does R change if the body temperatures are converted to degrees Fahrenheit? Well, let me help you out with this one because it's not something that you're expected to know. But if you change the scale of this, it's still not going to change the correlation. Body temperature is not related to the circumference of your head. It's just not. So if you use Fahrenheit or Celsius or Kelvin for that matter, it's not going to change. So rescaling it won't change the fact that they're not linearly related. So are we okay with those first few examples?
What's the answer for C?
Oh, the answer for C is C.
Okay, thank you.
Yeah, thank you. Yeah, the value does not change because R is not affected by converting all the values of a variable to a different scale. They're still not linearly related. So still a good correlation of 0 or close to 0. Thank you. Now, let's take a look at example B. Now, I've taken the liberty of drawing in some lines here. This is a good test problem. I mean, it typically occurs on a lot of my tests. And the idea is to do a little bit of matching. Try and match the data with the correct linear correlation. So you got 5 plots, 5 different values of R. What I would suggest you start out with the one that's most obvious. So which one of these colored plots, 1 through 5, looks like, okay, I know this one's got to be this. Which one's the giveaway?
Could it be scatter plot 5?
Yeah, scatter plot 5 looks really close to
-1.
-1. And there's one of these values that's really close to a perfect linear relationship. And that's this one. So yeah, perfect, spot on. Where would you go from there? I mean, there's a lot of possibilities. I mean, let's focus in on this. There's only 2 values that correspond to positive correlations, right? The first one and the third one. So which one of these is going to go with scatter plot 1? Which one's going to go with scatter plot 2?
I think that scatter plot number 1 will go with the third choice, 0.788.
Okay. So if you look at this, I mean, you have a choice of a correlation coefficient of 0.4 or call it almost 8. So 0.8 should be pretty close to a straight line, which, you know, this isn't too bad. And I agree with you. It should be something closer to 1 than not. And so that gives me kind of another one for free. There's only one other plot that has a positive correlation, which would be this one. So we got 3 down, 2 to go. So between scatter plot 3 and scatter plot 4, we got to come up with these other 2. Let's look at scatter plot 4. You've got a choice of either -0.414 or -0.788. Which one do you think this one looks like? -0.788 or -0.414?
-0.788.
Awesome. Thanks, Marge. There we go. -0.788. All right. So those are our different correlations. And it's measuring the strength of a linear relationship. Let's just double check this last one, make sure it makes sense. I mean, I guess if I had to draw a line, it looks like it would be going down, kind of. I mean, the data is kind of random. It looks more like a 0 than anything else, but it does seem to have a little bit of a downward trend to it, giving it that negative, negative 0.414 is our only choice. So yeah, I'm pretty comfortable with those there. Okay. We're all right with example B? All right. Let's keep going. So we're going to do a scatter plot and conduct a hypothesis test. Now, our hypothesis tests in this section are going to be of the form of a correlation being 0 or not. Either there is a correlation or there is not. So let's see. Oops, wrong one. There we go. Example C. Why did that do that?
Word popped up on your screen.
Yeah, which is weird because I wasn't even touching my computer at all. Maybe I breathed on it wrong. I don't know.
It's the aliens from your background.
Yeah, there you go. Now in this section, you're going to be testing rho equals 0 versus rho is not equal 0. So that's going to be our step 1. This says there's no correlation. There's none. There's no linear relationship between X and Y. And this says there is a linear correlation. So, all right. So we're going to be testing these two different hypotheses. The hard thing to keep in mind is this second part. That is, if there is a linear relationship, then rho is different than 0. That's seeming a little bit challenging for some reason. Let me go back to example C. Let's work through this. It says graph the data as a scatter plot. Find the linear correlation coefficient and then determine whether there's sufficient evidence to support the claim of a linear relationship between the two variables. So I'll start with the first part, which is a scatter plot. And of course, I got to give you some data first. Were you guys able to get the data last time into your
Yes.
stat disk?
Yes.
Yes? All right, that's good. So let me put the data into the chat here. I hope that if you're not able to get the data that you let me know, so we can try and work around that. If I need to, I'll post it in D2L. All right. So let's go back to stat disk. And I think I actually have the data already pasted in for myself. Let me just double check that. Yeah, I think it's there in the first 2 columns. Is that matching your data? First 2 columns?
Yes.
Yes.
Thank you, thank you. So let's go to data and then scatter plot. So I'm just writing a command down on our handout, data, and then scatter plot. It's going to ask you what you want the scatter plot of. And I want it in columns 1 and 2. Title, let's see, we'll call it first scatter plot. You can title it anything you want, whatever works for you. All right, so if I want to, I can redo this without showing the line there. So you just uncheck this, show the regression line. Maybe the regression line's helpful, but we're looking for a linear relationship. What it seems like to me is that if we had a little bit more data, this would come back down here and it would look like a parabola, not a nice linear relationship. As it stands, there is a reasonable line that kind of summarizes a lot of our data. Does it summarize it perfectly? No. But can you get away with saying there is a bit of a linear relationship? Yeah, I guess if you close one eye, close the other eye, close both eyes, there is a little bit of a linear relationship. We don't have to rely on just kind of an eyeball test of that. We can actually do a formal hypothesis test to see if there is a linear relationship. So let's do that. Now, I don't think I've given you a handout for this, but our steps are still the same. Step one, we're going to test if there's a linear relationship. We start by assuming that there is no linear relationship. And if we can reject that, then great. So, no linear relationship. And this is linear relationship. Step two, I'm not sure if they said it, but even if they didn't, we're going to test this at the 5% level. Step three, we're going to input our data. Step four is going to come from StatDisk. And let me write down the commands. It's going to be analysis. Is anyone surprised on that one? All right. And then go to correlation and regression. And from there, we're going to get our p-value. So let's see what our p-value is for this one. Analysis, correlation, and regression. Columns, well, I want 1 and 2. 5% significance level. I think we're looking pretty good. All right, so the correlation coefficient, that's 0.81760. That's pretty good. Means that there's a pretty good linear relationship between those two variables. Even though it looks more like a parabola, that's beyond the scope of this course, is fitting a parabola there. It's not hard. But what information do I need out of this right here?
The p-value?
A p-value. So the p-value is 0.00221, or excuse me, 211. And the thing about the p-value is that alpha, which is 0.05, is greater than our p-value, which is 0.0021. So when the p-value is low, H naught must go. In other words, reject H naught. Now it's kind of hard, but we got to figure out what the original claim is. In my eyes, we're testing to see if there is a linear relationship, so we're testing this claim. I'm going to consider that my original claim. And in part, I'm doing that for purposes of being able to state my conclusion. Now, moving forward in the course, it's not going to be as easy to use the wording, the conclusion to your hypothesis test as it was in chapters 8 and chapters 9. We're going to start doing other kinds of tests for independence, tests for goodness of fit, and it's just not going to work as well. Wording.
Professor Perry,
Yeah, Shane.
wasn't stated in that question. Do we just assume that it was 0.0?
I'm making that choice right here based on this is determine whether sufficient evidence to support the claim of a linear correlation between the two variables. So right there, support the claim of a linear correlation between the two variables. So that in my mind, if we're testing the idea that there is a linear correlation, that means rho is not equal to 0. And that's why I'm putting that there. So good question, Shane. I hope you.
Wait, I meant like alpha or the significance level?
Oh, yeah. That one I just chose. Yeah.
Okay, that's what I meant. All right.
Yeah, you're free to choose whatever you want if they don't give it to you. But typically it's going to be 0.05 or 0.01, one of those two. So, and actually in this case, it wouldn't make a difference because the p-value is low enough that you would reject either way.
Thank you.
You're most welcome. So step 6, the sample data support the claim that there is a linear relationship between the two variables. Yay. The one thing I want to point out is just because there's a linear relationship doesn't mean that one of these causes the other. Let me give you an example of what I mean by that. And for that, I'm going to turn to something that I don't think I gave you on one of your handouts. And let's take a look at, say, this one. You've got two graphs here, divorce rate in Maine and per capita consumption of margarine in the US. And if you look at those, they go pretty close to each other. If you look at consumption in pounds and divorce rate per 1,000 people in Maine, when one goes down, the other one goes down. When one goes up, the other one goes up, and then back down again. It's amazing how closely these track each other. But in a world that's filled with data, if you look hard enough and long enough, you're going to find these kind of crazy things. Does anyone think that if there's a dip in the divorce rate in Maine, that that's going to cause butter consumption to go down? I don't think so. Are they correlated? Yes. But does one cause the other one? No. And let me give you another example like that. There's a strong correlation between how much TV you watch and how much you weigh. People who watch more TV tend to weigh more. But does watching TV cause you to gain weight? What do you think?
No.
I don't think
Hmm?
so.
No, watching TV does not cause you to gain weight. What causes weight gain is consuming more calories than you burn. And if you're watching TV a lot, it's hard to burn a lot of calories. So there's a correlation there, but not a causation. And you got to be careful about that. We're going to talk about causation after Thanksgiving. But let's do one more example here. There's an example like this in the book. Now they give you a plot of some data like this. And what I had to do for myself is actually go through and type out all the different pairs of data. Now keep in mind, when you're looking at pairs of data, it's just going to be X and Y. All right, so X coordinate, then the Y coordinate. So here, for instance, is X equal 8. Then we got X equal 10, X equal 9 in between. So you got all these pairs of data. We're going to do a hypothesis test to see if there's a correlation between X and Y. So again, let me give you some data, save you a little bit of typing. Like that. Now the last value that I put here is for this point. And let's see here. Let's put that in the chat. There you go. Now we'll put that into StatDisk. I'm going to put it in columns 5 and 6. You can put it in whatever columns you choose. Whew. I'm also going to double check that these columns don't have any hidden characters. They don't seem to. So we're good there. Now in the previous example, I took the time to do a scatter plot. I think that's part of the output from our regression, so I'm not going to take the time to do a separate scatter plot. We're going to test row equals 0 versus row is not equal to 0 at the 5% level. We've already input our data, so that's step 3. Step 4 is to find the p-value. That's also going to tell us a little bit more about our data. So analysis, correlation and regression. For me, it's columns 5 and 6. And wow, take a look at that p-value. Step 4, our p-value is 0.00051. That's going to be significant at any level. Step 5, reject H naught. Step 6, there's a significant linear relationship between these two variables. But that's not really the point of the problem that they give you here. And I'm not going to bother stating this in words. There is kind of a real point to this. It says remove the point at 1 and 9, and then find R again. So what they're trying to show you is just how influential of a point this is. So if you wanted to, you could look at the scatter plot. They fit a nice linear regression there. Looks pretty good. We got a highly significant value of R there. But let's just go back and take out that one point, and we'll rerun things again. So hit the delete key or backspace so you don't leave any characters there. Then I'll rerun that analysis again. Hypothesis testing. No. How about correlation and regression? There we go. And it was columns 5 and 6. Now what do we get? P-value of 1. Wow. You'll never see that in working with real data. It's just crazy. But what's that tell us about our regression here? Or about the correlation?
It's positive.
You gotta be careful. We need to look at this line.
Not linear at all.
Yeah, it's a flat nothing. If you look at your scatter plot, you'll see why. I mean, the line that you would fit there is exactly horizontal. You've got points all over the place that are equally spaced, not up, not down. It's just flat. So we got a correlation of 0. There's no linear relationship. There's no relationship between X and Y at all. It's just a big mess. So what that's saying is that after you remove that one point, the correlation is 0. That means that one point was highly influential. And there's actually ways you can quantify that. But the conclusion is the point at 1,9 was very influential. And what's happening when you take out that point is the correlation goes from, you know, a highly correlated 0.8 something down to 0. So, okay. That's all I got time for. Is there any follow-up questions on this last one here? All right, hope you're in good shape for this section and for the break. Have a great holiday and see ya.